Good morning, I'm Stefan Werkstätter, VP of Sales, EMEA at EPC. Welcome to today's webinar, Revolutionizing Audio Amplifiers, Unleashing High Fidelity with EPC GaN FETs and ICs, where we will provide comprehensive overview of Class-D audio amplifier applications, highlighting how EPC GaN FETs can be leveraged to achieve compact, efficient, and high-fidelity solutions. Before we get started, I would like to go over a few housekeeping items for today's event. You will have the opportunity to submit text questions to the panel by typing your questions into the Q&A feature at the bottom of the screen. You may send in your questions at any time. We will collect these and address them during the Q&A session at the end of today's presentation. Now I would like to introduce our speaker today, Tiziana Morganti, who is Staff Applications Engineer in Europe.
Good morning to everyone. Today's webinar, we will talk about the Class-D audio application with our GaN FETs and the new demo board EPC9192. Brief agenda for the webinar. So, audio amplifier market overview, the challenges of audio amplifiers, Class-D amplifier introduction and requirements, EPC GaN FETs for Class-D audio, and then we will talk most of the time about the EPC9192 demo board. So we will go through the design, thermals and efficiency, and show some audio performance measurements. So the audio market is divided in three main segments: home, professional, and transportation. So in home market, we have sound bars, hi-fi amplifiers, home cinema sets, and subwoofers, and so on. For pro audio, we have fixed install amplifiers, touring amplifiers, powered loudspeakers. Many of them are using Class-D audio power amplifier modules like this one, and music instruments. And for transportation, we have automotive audio, so amplifiers in cars, and also in vehicles in general, like boats or AGVs. In terms of GaN adoption, we find a growing interest in GaN as a way to reduce the losses, the weight, the size of the amplifier, both in home, so hi-fi amplifiers, and pro audio, multi-channel amplifiers, and also car audio. The main challenges depends on the power level of the amplifier. So at low power level, most likely they are portable devices. So you need long playtime with battery-powered portable devices. In all home systems, the number of channels is growing to implement immersive audio and multi-channel systems. And also the consumer audio products market is very price sensitive. In the mid-power range, we are talking about power level above about 100 or 200 watt per channel. So this is a power level that is often not possible to reach with integrated circuits. Thermal needs careful design to reduce also cost and size of the device. So it's important to get a low loss solution. For the high power market, so we are talking above 400-500 watts up to few kilowatts per channel. So this is the realm of pro audio amplifiers. So it is important also, it is even more important the heat sinking, and of course at this power level heat sink is required, and often with forced air cooling. So it takes usually a lot of space. So the highest is the efficiency of the amplifier, the smaller can be the heatsink and the size of the product at the end. And also, most likely, the voltage ratings of the power devices is above 100 volts, so the 150 or 200 volt rating, or even higher. And the main challenge is that in case of silicon MOSFETs, those higher voltage devices struggle with switching performance. So very brief introduction. So what is a Class-D amplifier? So Class-D amplifier is a switching mode power amplifier. So there are switching devices. So this is an example, an half bridge power stage. And there is PWM modulator. Very simple example here. It's a comparator comparing the analog audio input with the triangular wave. But of course, it's more complicated than this example in practice. So basically, the analog input signal is converted in a PWM modulated high frequency signal that is then amplified by the say digital power stage, and then it's low pass filtered and converted back to the amplified version of the analog input. So EPC is working on the power devices. So it's providing the power devices and also the power stage. So integrating also the gate driver. So what are the main requirements for a Class-D amplifier? So in order of importance, we have the power output. So this is the main data, target data that, so basically we have peak voltage, peak current, rated power. In terms of audio performance, they need to achieve low output noise, low total harmonic distortion, intermodulation distortion, and wide bandwidth to cover the 20 Hz to 20 kHz audio bandwidth. And in terms of heat sinking, so we need to reduce as much as possible the heat generation, so the losses in the amplifier. This is important both in idle or with very low power output, so no signal output or very low power output, because most of the time the audio amplifier is operated at low power. But it's also important to optimize the losses while delivering the rated power, because this is driving the size of the heatsink and the fan or ventilation requirements. And also, size is also a very important parameter for the design, because in the last years, the number of channels of audio applications has grown a lot. And also the power requirements are continually increasing. So it's important to squeeze the size of the amplifier to fit more channels in one device. So regarding the power and how it relates to the power device selection, so we have if we have specified the sine wave rated power output, so this is equal to the square of the peak voltage divided 2 times the load resistance. So this is so given the power output and the load, you can obtain the peak voltage, and this is related to the VDS rating. So in case of an half bridge topology, the VDS ratings is 2 times the peak voltage plus some margin. In case of full bridge topology, the VDS ratings is equal to the peak voltage plus some margin. So an example, for 100 watt at 8 ohm, a 100 volt device is okay. It's barely okay. So it's a 40 volt peak, this power level on 8 ohm. for an half bridge. For 450 watts on 4 ohm and an half bridge configuration, you need 150 volt device. For at the upper extreme 3000 watt on 4 ohm, you need a full bridge with 200 volt devices. In terms of current, the peak current of the amplifier is equal to the peak voltage divided the load plus some margin, because the load can fall in some region of the audio bandwidth below the nominal resistance. So you need some overhead to drive the load. So this peak current is driving then the selection of the power device in terms of RDS on and of course the thermal resistance and the thermal design. And this comes with parasitics, so gate charge, output charge, and reverse recovery charge. So it is in terms of device selection, it is not trivial to select a low RDS on device with high VDS ratings and with good switching parameters. So including the body diode. So in terms of silicon MOSFETs, it's tricky and challenging to select the right device. So what EPC is offering is a better power switch. So basically, we have our GaN technology. We can offer lower losses. So we have lower RDS on and lower switching losses, and compared to the best silicon MOSFETs, we can offer 4 to 10 times lower losses. This translates into a smaller heatsink, or in some cases also no heatsink. And this is also meaning lower requirements in terms of ventilation. So we can design the amplifier with lower speed and quieter fan, or eventually convection cooled. Also, we can offer higher switching frequency. So this translates into smaller and less expensive inductors for the output filter, and also the opportunity to implement a better control loop to achieve better audio performance. In terms of audio quality, our devices are switching very fast, and they offer pretty much ideal switching waveforms. So we have a better open loop linearity compared to power silicon MOSFETs. So all of these can provide a solution that is future-proof, quieter, smaller, and lower consumption. In terms of example, we are comparing very used silicon MOSFET. It's a 200 volt, 22 million typical, with some of our devices, EPC 2215 and EPC 2307 in QFN package. So you can see the improvement over silicon is huge. So we have 3 times lower RDS on, much smaller gate charge, and more or less the same output charge, but with much lower RDS on. We have no reverse recovery, and also the device size is 10 times smaller. So these parameters can guarantee lower losses at higher switching frequency. In terms of losses comparison, the silicon device compared to the EPC 2215, so we have the worst case scenario, so it's the peak of the sine wave where we deliver the full output current for maybe short term, meaning that at low frequency, this area here can last maybe 10 or 20 milliseconds. But in this worst case scenario, the silicon MOSFET is dissipating about 90 watts of losses. And the EPC 2215 is the loss is reduced to 13 watts, mostly because of reduction of the conduction loss and the reverse recovery loss. And then in the sine wave power, so 3 dB crest factor for a 600 watt amplifier, it's about 25 watt of loss per MOSFET in the silicon case. For the GaN FET, it's about 5.5 watt of losses. And while in case of more realistic signal, so this is a 9 dB crest factor, so it's about 1/4 of the duty for the sine wave or pink noise with 9 dB crest factor. The average losses for the silicon MOSFET is 8.5 watts compared to 3 watts for the GaN, and also at 12 dB crest factor, 6 watts compared to 2.5. Also, in terms of idle losses, the loss related to the gate drive for silicon is relevant. So we have about 0.8 watt of losses for the silicon MOSFET. This is excluding the losses in the inductor, which is the main part of the loss in idle. For the GaN FET, the loss is almost negligible. It's about 0.1 watt. So this is because of the much lower gate charge of the GaN FET. Okay, let's talk about the EPC 9192 demo board. So what were the design goals? So first of all, we wanted to address the medium to high power range of applications. So we are not going to compete with low power IC-based solutions. So we needed to reach compactness of the solution, so small solution, high efficiency, so low idle losses and high full load efficiency was the main requirement, main design criteria. We had to achieve good audio performance in terms mainly of low noise, the first priority, low distortion, but this is usually less audible, so we didn't want to compete with the best state-of-the-art very low distortion amplifier in the market, but still reach inaudible levels of distortion. And also low output impedance, because this can guarantee frequency response that is not dependent on the load, and also much lower crosstalk between channels. And also we wanted to provide a solution that is easy to customize and to modify according to the designer needs. So this is the eval board. It's built around a reusable motherboard that it can accept up to ±85 volt supply, and it has all the housekeeping supplies, protections, and the connectivity, input-output connectivity, and for the power supply. Then we have a daughter board with the PWM modulator, which is this one. And the kit is coming with self-oscillating post-filter feedback based modulator running at about 600 kilohertz. And also there is another daughter board, which is the power stage, which is an half bridge with the output filter included. So going a little bit in detail, so this is the main board. So we have the audio inputs and the front end with both balanced and unbalanced inputs. We have the housekeeping power supply. So you provide 12 volt here, and you have minus 12 volt and the gate driver voltage generated by two DC-DCs. And you have under voltage protection, over voltage protection, over temperature protection, and over current protection. It hosts two PWM modulators and two power stages. So those are the inputs, balanced XLR and unbalanced RCA inputs. We have speaker outputs on terminal blocks, the 12 volt input terminal block, the high voltage dual DC power supply. This is the all current sensor for the overcurrent protection. And we have some jumper to configure the board in BTL mode, unbalanced mode. The gain, input-output gain, can be set to about 20 or 30 dB, and to keep the power stage in shutdown. So this is the PWM daughter board, and this is the power stage daughter board. So let's talk about the power stage. So this is the power stage, is about 5 centimeters by 5 centimeters. It is based on the QFN EPC FET EPC2307, which is 10 milliohm max 200 volt. The gate driver is an on-semi NCP 51820. It is designed to offer good PCB cooling, and it can work actually without the heatsink at the rated power, or for full power, there is an heatsink option. In terms of capability, it can deliver 80 volt peak, 30 amp peak, so it can drive comfortably 700 watts on 4 ohm or 370 watts on 8 ohm. This is an overview of the schematic of the power stage. So we have a level shifter to the negative rail. So the PWM signal from the modulator is referred to ground, while the gate driver is referred to the negative voltage, supply voltage. Then we have, we drive the PWM to the gate driver inputs, and the gate driver is taking care of the generation of the dead time. Then we have another level shifter for the enable signal, and we have to drive the enable input of the on-semi gate driver with low impedance to avoid noise coupling to the enable input. Then we have bootstrap power supply for the high side gate driver. So the on-semi gate driver has an internal low dropout regulator. So we can provide a 12 volt supply to the gate driver on both the low side and the high side. So this is useful to allow some not well regulated bootstrap voltage that is typical for Class-D audio due to the wide range of the duty cycle. And we have an additional 10 microfarad capacitor to improve the hold time in case of clipping to the positive rail to about 50, at least 50 milliseconds. And we have some pre-bias circuit to start with the gate driver already operational from the first cycle to avoid glitches at the startup. Then we have the dead time setting. It's a pretty long dead time because it has been optimized for low idle consumption. It's 50 nanosecond dead time. Then we have Schottky diode for a reduction of the distortion and also a reduction of the losses in the GaN FETs in the freewheeling time during the dead time. Then we have a temperature sensor for over temperature protection, which is connected to the source of the low side FET to have it very close coupled to the FET. Then we have a two-stage output filter. The first stage is mainly for EMI reduction. It's a very small inductor, 313 nanohenry, with a snubber. And this is filtering out the noise above 20 megahertz. And then we have the main inductor, which is edge-wound inductor, 10 microhenry, 40 amp saturation current. And then we have a field capacitor for the output filter. So talking about the power stage, let's have a look to the layout we implemented. So it has been routed on a 4-layer, 2 ounce per layer PCB. Components are only on the top side. Here are our GaN FETs. Those are 3 by 5 millimeters. We used via-SIM pad, and we were able to fit 48 via-SIM pad for each FET. And this is very important to reduce both the parasitic inductance and the thermal resistance to the internal copper layers. So we have the layout, which is implemented as internal vertical layout with middle capacitors. So those are the 4 high-frequency capacitors, which are rated 10 nanofarad, 200 volt in 0603 package. And if we, so we have the extra Schottky diodes, and we have then the medium frequency bypass capacitors. So those are 1 microfarad to ground, 2 of them, and 100 nanofarad across the positive and negative rail. This is the gate driver, low side and high side. So we can go through the layout and start from the positive terminal of the power supply. So from the high frequency capacitors, so we go to the drain of the high side FET, then we go to the source of the high side FET, we go to the first inner layer, we have the switching node connected to the source of the high side FET. The switching node is going back to the drain of the low side FET. Then we return to the source of the low side FET, and we close the loop directly on the high frequency capacitor. So you can see the commutation loop is very short, it's wide, and it's implemented in the 2 upper layers of the board, which are spaced by 0.2 millimeters. So the power loop inductance in this way is quite limited. And also we have the high side gate driver very close to the gate. The return path is both on the top side and on so the switching node polygon has been extended below the gate driver for the gate driver return path, and in a similar way on the low side FET. In terms of the thermal design, yes, the 2 ounce copper is helping to spread the heat from the device. So on the top side, you can see the copper polygons from the high side device and the low side device. And then we have a lot of via-SIM pad that are bringing the heat to the inner layers of the PCB. So we have copper polygons duplicated also on the bottom layer of the PCB to spread the heat. And also we placed 1206 copper jumper as heat spreader on the drain pad of the device. And this is helping to transfer the heat also to the heatsink. Those are the mounting holes for the push-pin heatsink. We have the position of the temperature sensor for the over-temperature protection. You can see it's close coupled to the low-side FET source. And then to mount the heatsink, we have a 10 by 15 millimeter gap pad with very high thermal conductivity. And then the heatsink is assembled by plugging the push pins in the two mounting holes. So in terms of thermals, so we have a few example conditions. First one is no heatsink, no ventilation supply at plus minus 48 volts. So this is and 4 amps of output current. So this is 125 watts on 8 ohm sine wave power, or 250 watt on 4 ohm 9 dB crest factor. So you can see the temperature of the FETs is about 78 degrees. The PCB is 66 degree, close to the FETs here. The inductor is 61 degrees and the ambient was 25. So this is a more challenging condition, no heatsink with some ventilation, not very strong airflow. The rails are at plus minus 70 volt, 5 amps RMS of output current, which is about 200 watts on 8 ohm sine wave power, or 400 watts on 4 ohm 9 dB crest factor. So you can see the FETs are at 110 degrees, the PCB is 69, the inductor is 53, so the airflow is working to reduce the temperature of the inductor also, and the ambient still 25 degrees. Another condition with the heatsink and no ventilation at plus minus 70 volt supply rails. So same condition as before, 200 watt on 8 ohm sine wave, or 400 watt on 4 ohm 9 dB crest factor. So you can see here without ventilation, basically the full assembly is getting hot. So the heatsink is 83 degrees, PCB is 73, and the inductor is 86 degrees. So basically, in this condition, the thermals are limited by the small size of the power module, and so by the resistance to ambient of the whole power module. Then we have with heatsink and airflow at plus minus 82 volt supply rails, 10 amps RMS output current. So this is 350 watt on 8 ohm sine wave power, or 700 watts on 4 ohm 6 dB crest factor, which is a pretty dense music signal. Maybe in some subwoofer application you can find such a dense signal. So we have the heatsink is 71 degrees, the PCB is 61 degrees, the inductor is 56 degrees. You can see the hottest area is the PCB close to the Schottky diodes, which is 84 degrees. In terms of efficiency, we measured efficiency in the low power range. So we have, let's say, confirmed the low idle losses. So this is 40% efficiency at 1% power output, so which means let's say at plus minus 82 volts, 5.2 watts of losses. So to be noted that the efficiency is not much dependent on the supply voltage. And then let's have a look to the efficiency at full load or high power. So we could reach about 96% efficiency at rated power. Example of the switching node waveform. So this is the amplifier with 20 amps output current on a 2 ohm load. So it's about 40 volt. So this is 50 volt per division. So this is about 40 volt output at 20 amps. Power supply was plus minus 82. So you can see the low side FET is turning on. You can see here some freewheeling during the dead time. Then we have the high side turn on in hard switching. So you can see very little overshoot. So it's a very clean waveform. Then you have high side turn off, freewheeling with very clean waveform also, dead time, and then low side turn on. If we zoom in the edges, you can see the hard switching waveform here. This is 20 nanosecond per division. We can see some effect of the recovery here in the Schottky diode. This is a topic for a next investigation we have to do. But the waveforms are very clean. So let's talk now about the audio performance. So this is the frequency response we measured on various loads. So open 8 ohm load, 4 ohm, and 2 ohm. So you can see the frequency response is pretty much independent from the load. It's to be noted, this is 0.2 dB per division, so it's very flat. So 20 Hertz to 20 kilohertz, there is maybe less than 0.5 dB drop at 20 kilohertz. And the output impedance was measured to be pretty low. So it's about 8 milliohm at 1 kilohertz and about 25 milliohm at 20 kilohertz. This is the THD plus noise versus output power. So you can see at 100 Hertz and 1 kilohertz, it's pretty low. It's rising a little bit at 7 kilohertz, but it's, I would say, a good result. Then we have THD plus noise versus frequency. So you can see it's not increasing a lot with frequency, so it's pretty flat THD plus noise. And then noise floor FFT. So we measured 38 microvolt A-weighted noise output at plus minus 82 volt. 85 actually, 85 volt supply. So this is corresponding to more than 122 dB of signal to noise ratio. This is the FFT with 1 watt output on 4 ohm at 1 kilohertz. So we have a THD of 0.003%. This is FFT with 2 sine waves, 18 and 19 kilohertz, 5 watt on 4 ohm, and this is corresponding to a CCIF IMD of less than 0.04%. Okay, so areas of improvement there are, but let's say that we got a pretty good starting point. So we have to investigate what is the effect of the Schottky diode. So if they are actually adding losses to the switching behavior. So we have to investigate what happens without the Schottky diodes. We have also to investigate about the dead time related losses. So we are using a pretty long dead time of 50 nanoseconds. And this was driven mainly by the use of an off-the-shelf inductor, which is limited to 10 microhenry and not lower. So we had to run a pretty long dead time for optimizing the idle losses. And of course, you can use also dead time setting that is adaptive depending on the output current, and that this would help to reduce the losses related to that time. The inductor can be improved with a custom design. So we can use lower inductance that can then allow lower setting of the dead time and also lower losses. Noise, it is a pretty good result, but can be improved. In example, the input stage on the motherboard and also on the modulator board is not super optimized for low noise. So we can use better operational amplifiers and also lower value resistors to reduce the noise in the input stage. And also we can push a little bit more the higher the feedback loop gain at lower frequency to reduce the noise in the output stage. And then THD can be certainly optimized, and this is most likely coming from a reduction of the dead time. And also we have seen the layout with the motherboard and the PWM modulator that is separated from the power stage is not helping to keep, let's say, low coupling between the two channels. So in this board, we are running one of the two channels about 20 or 30 kilohertz higher switching frequency than the other to avoid coupling beating tones. But certainly by optimizing the layout of the motherboard and this effect can be reduced. Okay, so as a summary, we talk about the adoption of GaN FETs in Class-D audio, and this is really speeding up in the last couple of years. EPC has the widest selection of GaN in 100 to 200 volt range. Our GaN FETs are enabling low loss, high power density, and let's say next generation amplifiers for future solutions. Our demo board EPC9192 is a good starting point both for evaluation of GaN technology and for starting a design of a product. And we can offer support to address your doubts and your requests.
Okay, thank you, Tiziano. So now we're going to begin answering the questions submitted during today's presentation. And as a reminder, you can still submit questions by typing your questions into the Q&A feature at the bottom of the screen. Tiziano, our first question is, or there are two questions in one submission. Comparing to MOSFETs, what is the reason that standard dynamic parameters like TR, TF, TD on, TD off, and others are not published in EPC datasheets?
Yes, the reason is that we are offering those parameters are depending on the drive conditions, and with the speed of GaN FETs are also depending on the layout, because we can switch in below 1 nanosecond. So also the layout is affecting the rise time, fall time, and so on. So we are just providing SPICE models or models of the FETs, and I think it makes not a lot of sense to publish rise time, fall time, and so on.
I think this already answers the second part of the question. For reference, would you provide TR, TF parameters for eGaN used in the new Class-D amplifier or for any other eGaNs?
Yes, I think best way is download our models and simulate the solution. Of course, there is some attention to be paid to the parasitics, so you need to add the layout related parasitics in your simulation, and that will provide the best answer.
Okay, then next question is figure 16. Why is the built-in diode not suitable to limit THD and need D1, D2 external SD?
Yeah, okay. Yes, our eGaN FETs reverse conduction mechanism is offering recovery-free diode function, but the forward drop is a little bit higher than a PN diode. So it's between 2.5 3 volts, depending on the current. So the effect on the waveform is let's say bigger than for a PN diode, like the body diode of a silicon MOSFET. So the Schottky diodes are offering a lower drop, so they are helping to reduce a little the distortion. But of course, I think best solution would be to have adaptive dead times and reduce the dead time when the output current is higher.
Thank you. So the next question also, I think you have covered partially already. Have you created a functional LT SPICE or P-SPICE simulation for EPC9192KIT?
Yes, we have it. Mainly to simulate the modulator. And yeah, for the power stage, it has been simulated, and but it's always the end result needs to be validated with the measurements on the prototypes.
And what kind of load have you used for testing 700 watts?
It's a resistive non-inductive load, and it's not a loudspeaker, it's a resistive load. So I think it's built around several power resistors in parallel, but it's a resistive load, by the way. I don't know if what was the exact thing you wanted to know about the load, but it's a resistive load.
Yeah, maybe the person asking this question can.
Yeah, you can integrate. Yeah, if you need more.
Okay, then we have one last question. Can you explain the self-oscillating feedback topology that you used?
Well, yes. It's let me let me. I think it's better on the schematic. So let me get the schematic. Okay. Can you see my screen?
Not yet.
No. Where is the control? I lost the zoom control, Stefan.
Okay. It's the green button in the middle at the bottom. This share.
There is no green button at the bottom.
Okay.
It is, oh, maybe, oh, okay. Okay, can you see my screen now?
Yes.
Okay. Okay, so this is the output voltage. So this feedback point is taken directly from the terminal block of the speaker output. So we have a first inner loop, which is going this way. So this is a derivator made by this capacitor, and those this is an equivalent load resistor. So we estimate the derivative of the output voltage in this node here, and that is corresponding to the inductor current, AC current, basically. So we close a first loop with a comparator here. So we have some hysteresis. This hysteresis is used to set the switching frequency and to force the ripple current in the inductor to be within the range of the hysteresis. Then we have so this loop here will dampen the output filter resonance. So the output filter resonance is 10 microhenry and 0.68 microfarad. I think is around 60 kilohertz, something like that. So this circuit here is helping to improve the outer loop feedback. So this outer loop here is also taken from the output terminal, and this is implementing the feedback in the audio bandwidth. So those three resistors and this input resistor here are setting the gain of the stage. So this is an inverting amplifier, and we have a second order integrator here with clamping, and then this the output of the integrator, which is the error amplifier, is fed to the comparator. So this is an old patent. The technology was called mu-eta modulation. It's an old patent from Veltman, and it's expired today. So hope to have replied to your question.
Okay, so yeah, we do not have any additional questions. So thank you, Tiziano, and thank you everyone for attending today's webinar. So if there are any additional questions, please send them to info@epc-co.com. I repeat, info@epc-co.com. And you will receive a follow-up email within 48 hours with a link to view the recording of today's webinar. Thank you for joining us today and enjoy the rest of your day. Bye.
Thank you. Have a good day.